So have you ever wondered if it is possible to sort data faster than the standard sorting algorithms you use every day? What if I told you that under the right conditions, you can completely bypass the usual limits and sort an array in linear time? Hello everyone and welcome back to Techmine Guru. I'm your coach Supratim and today we are diving into lecture 24 of our data structure and algorithm series. Today's topic is count sort and merge sort, or as I like to call it, the art of order and optimization. So let us look at the agenda for today. We will start by covering the magic of count sort, including how to handle limits and negative ranges. Then we will look at what I call the Gmail problem, which is all about merging arrays. After that, we will take a deep dive into merge sort. And finally, we will compare stable versus in-place sorting to understand which tool to use and when to use that. Let us kick things off with a warm-up problem. Imagine you need to find the smallest number that can formed by rearranging a given set of digits. And the constant is that your array elements will be in the range of 0 to 9. So suppose in example 1, 3, 2, 4, 1 is there. You need to order it in 1, 2, 3, 4. So let's see one more example. Here, your array is 6, 3, 4, 2, 7, 2, 0. And when you reorder, it will be 0, 4, 6, 7. And this is what it will exactly look after you sort these two arrays. Till now, whatever solution you have learned using those sorting techniques, the time complexity will be O of n log n. But can we do it faster? Yes, because in this, values are strictly in between 0 to 9, right? So this is where we introduce count sort. The process is incredibly simple and involves two steps only. Step 1, you have to calculate the frequency of each value from 0 to 9. And in step 2, you will use this frequency array to print the final answer. Suppose your array is 1, 9, 8, 9, 7, 1, 1, right? So you will create a frequency array in the first step with all values initialized as 0. So how many zeros are there in this array till here? No zeros, right? So 0 zeros. How many ones are there? 1, 2, and 3. 3 ones are there. So in 1th place, the frequency will be 3. Similarly, how many 2s are there? No 2s, right? Similarly, 3 is also not present, 4 is also not present, 5 is also not present, 6 is also not. Finally, we will get 7 as frequency 1 and 8 as frequency 1 again. But since we have two 9s, so the frequency of 9 will be 2. Because we are just counting occurrences, the total iterations are basically n. This brings our time complexity down to an O of n only. And since the range is between 0 to 9, so our space complexity will be O of 10, which is equal to O of 1 only. So let's see the code for the same. So we have initialized a frequency array of size 10 with all the elements as 0. Now we ran a loop over the array from I is equal to 0 to n minus 1, and we will keep the frequency of every element in this frequency array, so that since every element is in the range from 0 to 9, so in this frequency array, all the elements will be initialized initially with 0, and using this for loop, we can update the frequency of that particular element. And finally, for storing or printing the value, we will iterate from d is equal to 0 to 9, since our elements can be in between 0 to 9 only, and inside that, we will run a loop on the frequency array. That is, we started a loop from for I is equal to 0 to f of d minus 1. So which will be the frequency of that particular digit, and we will print d. So if you take this previous example, 1, 9, 8, 9, 7, 1, 1. So let's see the dry run for the same. So we will have one frequency array, right, which is initialized to 0. So all the elements will be 0 at every index. Since in this case, index is defining the elements present in the array or not. So in the first loop, we are running over the array. So how many f of 1 is there? 3, right? When we iterate the complete array, we will get this frequency as 3. Similarly, how many 2 present in the array? 0. How many 3 present in the array? 0. How many 4 present in the array? 0. And similarly, when we will reach 7, we will get 1, 7, right? And similarly, we will get 1, 8 also. And also, while iterating the 9th element, we will get it 2 times. Now, in the second loop, since it is starting from d is equal to 0 to 9, right? So we will iterate over the range of the array, which is given from 0 to 9, right? So in that, we will run an inner loop, which will run from I is equal to 0 to that frequency of that element. So how many f of 0 will be there? 0, right? So this for loop will not work, right? In the next place, when d is equal to 1, we will check how many f of 1 is there. It will be 3 only. But we are running a loop from for I is equal to 0 to 1 element lesser than the frequency. So we will print 3 times 2. So it will be 1, 1, 1. In next, we will see for d equal to 2, since we don't have f of d, so this loop will not work. Similarly, for f of 3 also, this loop will not work. And similarly, till f of 6, this loop will not work. Finally, when we will reach to element 7, it will see the frequency as f of 7 as 1, right? We will print 7 one time. And similarly, we will print 8 one time. When d will be 9, at that time, f of 9 will be 2, right? So this loop will run from I is equal to 0 to 2. So it will print 9 2 times. So let's understand the time complexity. Since this first for loop is running from for I is equal to 0 to n minus 1, so there will be n iterations. So the time complexity will be O of n here. And in the next for loop, since this T is running over the range of the element, so it will be O of 10, so which is approximately equal to O of 1 only. And since this for loop is running over the frequency to print number of times the element present, so this will also run for n iteration. So in final, it will be 10 n iterations, right? And this is n. So our final time complexity will be O of n only. And what is the space complexity? Since we have taken one extra space of frequency array, so our space complexity will be O of 10, because we know in the initially only what is the range of the numbers present in the array. So the space complexity will be O of range of elements. But wait, what if your A of I is in the range from 0 to 10 to the power 9? Can you apply count sort still? No, right? Why? So let's take the frequency array size. So suppose the length of the frequency array will be equal to 10 to the power 9. And since we already know that every integer element in any language will take 4 bytes. So it will be 4 byte into 10 to the power 9 size of array. So which will become 4 GB or for that particular array only. So which will definitely give memory limit exceeded. So the golden rule is to use count sort only when n is much higher than the range of data. So the acceptable range is 10 to the power 6 to 10 to the power 7. So if A of I is in between 0 to 10 to the power 6 or 10 to the power 7, then only you can apply the count sort array. But now a question arises that your range is not starting from 0. It's starting from negative number. So how to handle the negative numbers and how to apply count sort when negative numbers are present? Because in the frequency array which we created, we treated index of that frequency array as the elements present for the input array, right? But in case of negative numbers, we cannot use negative indices, right? So for that, we will do some shifting. So suppose, for example, your range is between -9 to 9, right? So if you express that into a Venn diagram, it will be -9 to 9, right? What if you add +9 in both the places? Will it become positive? Yes, because now our new range will be from 0 to 18. So due to this code adjustment and shifting, now instead of updating the frequency array directly, we will update f of A of I plus 9, and 9 is the min element here. So the formula would be f of A of I minus min element. So what is the min element here? -9, and minus of -9 will be +9, right? But in this, while printing it, you will do d minus 9, because while storing in the frequency array, you subtracted that min element, but while printing, you have to add as well, right? So that the result is correct. So for that, while printing, you will do d plus min element. So finally, here also, what is the time complexity? It will be O of n only, and space complexity will be O of range of array. So here, range will be 18. So for handling negative numbers, just in this above code, you just have to replace this f of d to f of d plus 9, and in this, you have to do f of A of I minus min element, which was 9 here. So this formula will change into f of A of I minus min element, and this formula will change from print of d plus min element. So this is the minor adjustment you have to do when the range is between negative numbers and positive numbers. Now let us move to a different concept using an analogy we are all familiar with, the Gmail all inboxes feature, which you must have seen in your mobile or desktop. Suppose you have two accounts, account A and account B, and all the mails has been sorted with their timestamp. Mail number 1, whose timestamp is 1. This is mail number 2, whose timestamp is 5, and similarly 6 and 9. So if you just see the account A, it will be sorted that whichever came first. So this is 1, 5, 6, 9. Similarly for account B, you have 2, 4, 8. But if you have noticed in your all inboxes, all these mails are sorted in their respective time. So this is the direct application of merging two sorted arrays. So let us look at a problem. Suppose you have been given an array where all odd elements are sorted and all even elements are sorted in that array. And now finally the question says you to sort the entire array. So suppose you have the array in which after splitting into even and odd array, you get 2, 4, 8 and 10. And similarly in the odd array, you get 5, 11, 13, 15 and 21. So what will be the final output? 2, 4 will come before this 5, right? Now this 5 will come, then this 8 will come, this will not be there. Then this 10 will come, then this 11 will come, then this 13 will come, then this 15 will come, and then finally this 21 will come. So as we keep merging, we will check each element in both the arrays and we will compare and keep it in the final merged array. So let's understand the intuition for this. So when you have to merge even and odd, you will use the two pointer technique. First pointer will point to this array and the second pointer will point to this array. So the process is, first of all, you have to count how many even and odd elements are present. So what is the total number of even elements? Suppose it is n1. And what is the total number of odd elements? Suppose it is n2. Now you have to create two arrays where you will split the even numbers from length 0 to n-1 and odd numbers in the odd array from length 0 to n2. And finally, in the third step, you will compare each index using the two pointer technique in both the arrays, even array and odd array, and you will place the smaller result in the final array. So let's see the complete code for the same, and let's understand that with a dry run. So your sort array function is taking input of A. We are keeping the length of the array. Now suppose the given array was 2, 4, 8, 10, 5. So till here the even elements are sorted, and then 5, 11, 13, 15 and 21. Till here the odd elements are given. Since we have to count the number of even and odd elements, so n1 will tell the count of even elements and n2 will tell the count of odd elements. So first we will run a loop over the array from I is equal to 0 to n minus 1, and inside that we will check whether that particular element of that array is even or not. So we have used bitwise operator to check whether that element is odd or even. Since a of I and 1 will give the last bit as 1, which will indirectly tell that the element is not even. We will do n2 plus plus, which will count the frequency of the odd elements, and if this condition is not true, then we will increase the count of the even element. So this for loop will result in giving the number of odd elements and number of even elements. So now our n1 will be 4, right? And our n2 will be 5. Now we will split the input array into two arrays, one with the even array from length 0 to 4 and another with the odd array from length 0 to n2. So we have taken two pointers I and j, and here we are running a loop again into the array from for k is equal to 0 to n minus 1. We are checking if the element is odd or not. If the element is odd, we will put that element into the odd array. So we will start with the 2. So 2 will go in the even array, right? Then we will move to 4. This will again come to the else block. 4 will be going to the even array. Next, we will go reach to 8. We will move the 8th element to the given array. And finally, we will encounter 10, which is again even. So we will push that element into the even array. So our this pointer will reach here. Similarly, when we will iterate from 5, since all the remaining elements are odd, so all of them will go to the odd array. So this is how we splitted this array into two arrays, so that using these two arrays, we can finally merge them into a single resultant sorted array. So from here, we have copied all the odd elements to the odd array and even elements to the even array. Now we will start the merging process. So we have again taken the variable I, j and k. So I will track the pointers present in the even array and j will keep the track for the elements present in the odd array. So we are checking here while I is less than n1 and j is less than n2, and the element pointed by the odd array which is smaller. So in 2 and 5, which one will be smaller? 2, right? So in this case, we will move the even array pointer to the next element, and k will be pointing to our resultant array. Now k will move to here. Now again we will check 4 is lesser than 5 or not. It will say 4 is lesser, so we will keep in the resultant array 4, and we will increase again the even array pointer, and k will also increase. Now it will check whether 8 is lesser than 5 or not. It will say no. Now we will pick up the element from the odd array and we will keep the element in the final answer. So this time our pointer from the odd array will move from 5 to 11. That is in the next element. Then we will again check whether 8 is lesser than 11 or not. Since 8 is lesser than 11, so pointer pointed in the even element will move to the next element, which is 10. And also we will move our k to the next element. Now we will again check whether 10 is lesser than 11 or not. It will say yes. So again we will keep 10 inside the resultant array. And now since I will be greater than n1, so this while loop will break here. Now, so whatever the leftover elements will be there, we have to process them one by one. So since our pointer pointed by the even element is already crossed the length of the element present in the even array, so this while loop will not work for here, but our j pointer is still at one position, so which is still less than the length of the array. So we will run a loop from j to n2, and we will copy all the remaining elements into our answer array. So finally, we have understood that how we splitted our input array to two even and odd arrays, and finally we merged both the arrays to get the resultant array. So let's see the time complexity of the same. Since this loop is running from for I is equal to 0 to n minus 1, so the time complexity here will be O of n. Here we are splitting the array into two sub arrays, that is one even and one odd array. So here again the time complexity is O of n only, since we are running one loop only, that is from k is equal to 0 to n minus 1. And finally, when we have both the even and odd array, we are finally merging them using one while loop only, which is running from I is equal to 0 to n1 and j is equal to 0 to n2. So here also our time complexity will be O of n only. And finally, for the remaining elements, you can also see that they are also running individually O of n only. So what is the total time complexity? The total time complexity will be O of n only. And since we are splitting the array and then we are merging again, but in the middle we have used two sub arrays, so phase complexity will be O of n. So basically, this merging logic is the backbone of our next major topic, which is merge sort. So merge sort will use a divide and conquer technique. So it will build a top-down hierarchical division tree. So the concept is to divide the array into multiple sub-problems recursively and then merge them one by one. So the base case to stop the recursion is when the array size is 1, meaning when L is greater than equal to R. And for the recursive step, we have to calculate every time the midpoint, which will be given by the formula L plus R by 2. And then you have to sort the left separately, and you have to sort the right separately. And finally, you have to merge the left sorted and the right sorted array in the similar fashion which we have done in the previous exam. So let's see the code for this. The code is very simple. You will write a merge sort function which will take input of the array and the left pointer and the right pointer. So the left pointer initially will be at position 0 and the right pointer will be at length of the array, right? So this will work like our base condition which will stop the recursion. And every time you are going inside the merge sort, you will calculate your mid element so that recursively you can split the array. And then you will call the merge sort for the left array which is from length L to mid, and then you have to call merge sort for right array which will run from length mid plus 1 to R. And finally, you will merge both the left and the right array. So let's understand the code with this diagram. Your array is 9853641085. So here L will be equal to 0 and R will be equal to n minus 1. So which is 9 since we have 10 elements. So what will be the mid? So our mid will be 0 plus 9 by 2 which will give us 4. So here left merge sort will get called with the array and L as 0 and mid as 4, right? So this will again check whether L is greater than equal to R or not. So what is the array from 0 to 4? It will be 98536, right? Now in this, it will check whether L is greater than equal to R or not. So this condition will not work for this merge sort. Now this mid will be calculated again. It will be L plus R by 2, which is now the mid will be 2 here. Now it will call again the merge sort from A, 0 to 2. Basically, this will call 985 as the array. Now inside this merge sort, it will again check for the mid element. Now it will get mid as 1, right? Because L is 0 and R is 2. So it will call A of 0, 1. Again, it will call mid, which will now come as 0. So now it will call A of 0, 0. So which will be 9. So 9 will be the final element which we will get from here. So this will come out that the left side is already broken down and we have returned the control to this one. Now it will check in the right side. It will call A of 1, 2, right? Which will be 8 and 5. Again, it will get split to 2 elements, which will be 8 and 5. And again, it will come out. And since when both the left node and right node will be having single element, we will call the merge array. So we will see whether 5 is lesser than 8 or not. We will return here 5 and 8. And when 5 and 8 will be returned here, it will check with its left sibling. And in this, we will check and we will return 9, 8 and 5. And when the control will come to this 9, 8, 5, we will call our 3 and 6. And 3 and 6 will again get splitted. Again, merging will happen, which will result in 3 and 6 only. And finally, we will come back to 9, 8, 5, 3, 6. And similarly, when we return here, we will call the right subtree, which will be from A, mid plus 1, which is 5, and the R is 9. So it will be from 4, 1, 0, 8, 5, which will again follow the same process of splitting and then merging. So let's understand the merge code now. Since you remember from the previous code that before merging, you have to get the length of both the arrays. So what is the length of the left array? It will be from L to mid. And what is the length for the right array? It will be mid plus 1 to R. So as we already know that if we are given this range, so the N1 would be mid minus L plus 1. And similarly, N2 would be R minus mid minus 1 plus 1. So this minus 1 plus 1 will cancel out each other. And so the N2 will be R minus mid. So now we have to keep two auxiliary arrays, B of length N1 and C of length N2. And we will do the similar approach which we have followed earlier in case of even and odd. So we will run a loop from I is equal to L to mid, where all the elements will be copied from A of I to B array. And similarly, for the right array C, we will run a loop from I is equal to mid plus 1 to R, where we will copy array element to our right array. So when this left and right arrays are prepared, now we will run a loop from I is equal to 0 to N1 and J is equal to 0 to N2. And we will compare both right and the left array. Whichever will be smaller, we will copy that element to our resultant A array. So this will result in merging the left and right array according to if element is smaller or greater. And this is similar to what we did in case of odd and even array, where we copied the even array or the odd array on the basis of whichever was small by using two-pointer technique. And after completing the array, whichever are the remaining elements, we will simply copy the remaining leftover elements into that resultant array from that right or left array. So this merge logic is similar to what we learned in case of odd and even array. And apart from that, you just have to split the left and right array accordingly. So finally, when we reached here, when both the right and left merge sort comes out, we will start merging the array. So after we come to the left and the right array, we will simply merge it and we will get the sorted array. because this left array will have all the sorted elements, right array will also have the sorted elements. Now, when we have both left and right, both the arrays as sorted, we can apply this merge function, which will merge both the array in the final result where we will get all the elements as sorted. So, since we have already understood that this all functions were having time complexity as O of n only, since in every place we are running inside one for loop. So this is also O of n, and these three were also O of n. So this merge function will have the time complexity as O of n. So now let's analyze the total time complexity. So the merge function at every level will give the time complexity as O of n, and also we have log n levels to solve. So our total time complexity will be O of n log n. And what is the space complexity? Since in the merge array, we are taking two auxiliary arrays of B and C to denote left array and the right array. So the space complexity is O of n plus the height of the recursion tree, which is log n. So our space complexity will be O of n plus log n. So as we know, in time and space complexity, we ignore the lower order coefficients. So we will ignore the log n and the final time complexity O of n only. So before we wrap up today, we need to understand two technical definitions that often come up in interview related to sorting, which is stable sorting and the in-place sorting. So let's understand what is stable sorting. So suppose before sort, you have an array A is equal to 8, B is equal to C is equal to 8, and E is equal to 8. You have 5 elements with their marks, and after sorting, you will get A colon 8, C colon 8, E colon 8, B colon 5, and D colon 4. So you have sorted them with respect to marks in descending order. If you observe closely, the relative order of A in the input array and in the final array is not changing. Similarly, for C also, it is not changing. Since in the input array also, A is coming before the C and C is coming before the E. And you get exactly same thing in the resultant array also, where A is coming before C and C is coming before E. So if this kind of situation happens after sorting, where the relative order of elements is not getting changed, so in that case, we will consider it as a stable sorting. And what is in-place sorting? In-place sorting means while doing the sorting, if you use only O1 extra space and not On, then that will be considered as a in-place sort. So let us compare what we have learned today, that is count sort and merge sort side by side, and let's understand they are stable or in place. So as we already know, the time complexity in the count sort was O of n only, and in merge sort it is O of n log n. And what is the space complexity of count sort? It will be O of range of the array. And for merge sort, since we are taking auxiliary left and right array there, so the space complexity will be O of n. So how to determine whether count sort is stable or not, or merge sort is stable or not? So let's go back to the code again. So when we are doing analysis of the merge sort, we have seen that one condition that B of I is lesser than equal to C of J, which means the relative order in case when the elements are equal is not getting changed. So because of this lesser than equal to sign, we can consider that merge sort is a stable sort. But if we see our code for count sort, we will see you don't know whether this one is coming first or this one is coming. So you cannot determine that. So this will not be considered as a stable sort. So count sort, since we cannot determine which one will come first, so this will not a stable sort. And in the merge sort, we have already seen that when left array is lesser than equal to right array, because of that lesser than equal to sign, it is becoming stable. And since we know that the space complexity for the counts is O of 1 or O of range, so count sort is a kind of in-place sorting, but in merge sort, the space complexity is O of n, but in in-place sorting, we need O1 extra space only, so the merge sort is not in-place sort. So to master the art of order, remember this simple rule. Use count sort for small, tight ranges, and use merge sort for universal and stable scaling. That covers everything for today's session. In our next lecture, we will tackle quick sort and comparator problems. If you found this breakdown helpful, please make sure to subscribe to Techmine Guru and hit the like button. Till we meet again, keep coding, keep optimizing, and keep learning.